Okay, so 11.4, number 13. All right, oh no, 11.5, sorry, number 13. Okay, so disco Atwood machine. In the figure at the right, a wheel of radius 0.2 meters is mounted on a frictionless horizontal axle. A massless cord is wrapped around the wheel and attached to a 2-kilogram box that slides on a frictionless surface inclined at 20 degrees with the horizontal. The box accelerates down the surface at 2 meters a second squared. What's the rotational inertia? Okay, so here's our drawing. All right, so there are two objects that I'm interested in this problem. There's the pulley and the box. Okay, so for the box, here are the things that I know. Oh, I guess here. So here's your rope, and then the rope just winds around it. Follow? Okay, so for the box, here are the things that I know. We know that the mass of the box, which I'm going to call MB, is 2 kilograms. I know that it's going to accelerate down the ramp, so the acceleration of the box is 2 meters per second squared. I'm just going to draw a little arrow so that we know it's going down the ramp. You can call that negative if you want. I think I'm just going to call that way positive because that's the way everything's moving, sort of. Everybody good? Yeah. All right. Then for the wheel, what I know is it has a radius of 0.20 meters. And then the only other thing I guess I know is that this angle here is 20 degrees. Okay? And what the problem wants to know is, what is the rotational inertia of the wheel? All right? So, because the problem gives me information about acceleration, and it's looking at rotational inertia, intuitively, does it make more sense to solve it using total energy or net force and torque? Net force and torque, right? Because that's the piece that ties in acceleration, right? Okay? So what I'm going to do is I'm going to set up a system of equations. One system that explains what's happening to the box, and one system that explains what's happening to the wheel. Follow? All right? Now, when I look at the box, do I want, this is maybe a silly question, but it's a thing you got to make sure you process. Do I want to look at the torque on the box or the force on the box? Force. How about the wheel? Torque. Okay? So, any questions with what I've done so far? No. All right, so. All right, so for the box, let's think about what forces are going to act on the box. So shout them out. What do we got? I can think of gravity. All I really care about is FG parallel, right? So my FG parallel is the mass of the box, 2 times 9.8 times the sine of 20, right? So that gives you a number which I will calculate real quick here. 19.6 times the sine of 20 gives us 6.7, is that right? Yep. 6.7. 6.7 newtons. Are there any other forces? There's the tension in the rope. Now, there's only sort of one length of, well, I'm getting ahead of myself. Okay, so is everybody good with that? All right, so what I want to do is I want to use this information to write an equation, okay, that sort of ties together some of this stuff. So it's basically net force equals net force. So 2a, oh, I know that. I already know my mass and my acceleration, right? So I'm going to write it out just so that you know where I got this. So this is 2 kilograms times 2 meters a second squared equals the force of gravity minus my tension. Oops, why didn't I actually plug in my force of gravity? 6.7 minus my force of tension. Now, before you go any further, check your signs. Do all of my signs agree? Point for me. Which direction is the box going to accelerate in, you guys? Down the ramp. And I made that a positive acceleration, right? So that means anything going down the hill should be positive. Oh, and I made my FG parallel also positive, so we're good. Follow? Yep. Any questions on what I just did there? All right, so here is one equation. Oh, wait a minute. Oh, I can solve that, can't I? Yeah. All right, so let me pause for a minute. Sometimes, well, yeah, all right. So, sorry, I'm trying to decide sequence. Okay, so we can solve that, right? Okay, so if you do this, the tension force turns out to be a number. Anybody know what it is offhand? What is it? 2.7? Oh, right. 4, right. That's embarrassing. Okay. Yeah, so it's 2.7. All right, is everybody good with that? Okay, so I got lucky. I happened to stumble onto an equation that I can solve right away. And I'll be honest, when I set out to solve this, I did not know that. All right, so is everybody good? Yes.
When picking the signs, should you pick it based on the box or based on the torque from the pulley for the positive?
It's somewhat arbitrary. You sort of need to reevaluate your signs for each system anyway.
All right.
Do you know what I mean?
Yeah.
So, all right, is everybody good here? All right, so now the next thing I want to do is now I want to look at the wheel. So here's the wheel. What forces are acting on the wheel? Well, indirectly force of the box. What do we really call it though? Well, torque isn't a force. What's pulling the wheel? The box isn't touching it. So what's pulling the wheel? The tension from the rope, right? Oh, unfortunately, we just found that, didn't we? So, like I say, I got lucky when I solved this. So that tension force is 2.7 newtons. Cool? So, let me do this. So now I can, so what kind of equation do I want to write for the wheel? Not net force, but net torque. So let's see, net torque equals net torque. So that means I alpha equals the torque from tension, right? So do you guys all agree that the wheel's going to spin that way? Yeah. So let's just make that way positive. Cool? So let's see. I is the thing we don't know, right? Alpha. Pause. Think. What do we know about alpha? All right. So because the rope is attached to the box, the rope has to have the same acceleration as the box, right? Okay? And because the rope wraps around the outside edge of the wheel, that means the outside edge of the wheel has to have the same acceleration as the rope in the box. So my alpha should just be A, which was 2 meters per second squared, over R, which was 0.2 meters. So if you're keeping score, that was just alpha equals A over R. I used a jumper. Follow?
Yeah.
All right. Equals the torque provided by the tension. Well, that's force. The force of tension is 2.7 newtons times, what's my lever arm? 0.2 meters, because that's what my radius is, times the sine of some angle. All right, so does everybody understand that when you tie a rope around a wheel and pull the rope will always be tangent to the circle and therefore perpendicular to your radius? Sorry? So if you don't get that, then I want you to come up here and play with this later. So there's no way you can see this, but here, so look. Here's a wheel. Here's the rope wrapped around it, right? Here's my radius, right? So if I try to increase this angle, then what happens? The point of contact changes, right? If I increase my angle, then, now my point of contact is there, but still perpendicular. Follow? Okay, so I think we can solve this thing, can't we? So solve for I, and you're done. Good? All right, now, what will happen sometimes, and I know this happens in number 11, is you end up with 2 equations and 2 unknowns. All right, so here I had 2 objects, right? So this allowed me to write one equation. This allowed me to write another equation. All right, so sometimes you'll have 2 unknowns and you got to solve a system of equations. All right, for the really bad ones, you have 3 equations and 3 unknowns. Okay? But conceptually, you're just writing either a net force equation for an object or a net torque equation for each object. In a nutshell. Does that make some sense, you guys?
Yeah.
Okay. Questions on it? Yeah. Yeah. All right. Do I need to say anything else about number 13? Excellentorama. All right, let's talk about...